Ionic compounds typically consist of a metal and a nonmetal. And so an example of an ionic compound would be sodium chloride. One of the differences between an ionic compound and a molecular compound is what we think of as far as the charge on the atom goes. Here, ionic compounds are made up of ions. So this is a sodium ion and a chlorine ion. And so we just need to know the names of the ions in order to name these. This is a little different than, for example, a molecular compound. Well, actually, a little different. So let's talk about naming ions. Well, we have cations usually come first. Cations, this is cat. Ion. Cations are the positively charged ions. These come first. And then the anions follow. Next. Okay, these need not be binary. In fact, we're going to get into the more complicated ones. There could be binary ones like sodium chloride that's binary, but we'll do like sodium carbonate, which is going to have a lot of different elements in there. And so that's it. So what we want to do is we want to figure out the name of the monatomic. But the monatomic depends on if it's a cation or an anion. And this is where your supplement will come in handy. And so what we'll look at first are the names of cations and monatomic cations. Really monoatomic cations, we drop the O and just call it monatomic cations. All right, so let's look at monatomic cations. The name is just the name of the element. Okay. But we have two types of monatomic cations. We have something called fixed charge and variable charge. Okay, here I'm going to veer off from your PowerPoint. Okay, the fixed charge are going to be like this. Lithium. Lithium only has one charge on it. And what happens is lithium normally has 3 protons. So in the nucleus there are 3 positive charges. And then we have negative charges from the electrons. We have 3 electrons. And so the positive charge and the negative charge is balanced. But what happens is if we eliminate one of these electrons, here, let's say if it loses 1 electron by some means, then what we're going to get is we're going to get lithium ion. Lithium ion is going to have 3 positive charges and 2 negative charges. And the extra electron goes somewhere. So this would be the lithium ion. Now what do you think is going to be bigger? Which one do you think is going to be smaller? Lithium or lithium ion? Lithium's bigger. In fact, lithium's twice as big as lithium ion, roughly. And so when we lose that electron, the size shrinks dramatically. And so we end up with this, plus the electron. Now, which ones are the fixed charge? The fixed charge is what we call the main group. The main group elements are fixed charge. And so main group metals. And so, for example, group 1, which is the first column there, they all have +1 charge. So it's easy to figure out the charge. Sodium ion is going to be Na+, potassium ion is K+, rubidium is Rb+. This is group 1. Then we go to the next group. And the group 1 is called the alkali metals. And so the alkali metals have this +1 charge, but the next group is called the alkaline earth metals, and they have a different charge. Do you know the alkaline earth metals charge? You go to the alkaline earth metals. These are metals, ions, metal ions, I should say. For example, magnesium is a 2+ charge. Calcium is a 2+ charge. Strontium is 2+, etc. Then we hop over to group 13 because you know this middle block is not called main group. The main group, actually, let me show it on the projector. Easier to see. So the main group would be these first two. This middle block is not called main group. This middle block is called the transition metals. And this block here is called main group as well. And so another main group, although it lists aluminum as a metalloid, aluminum is more metal than metalloid, but it does have metalloid properties. And so aluminum is what we call fixed charge too. So we'll have aluminum 3+. Like that. All right. These are the main group fixed charge. Now the transition metals and the metalloids in general can have variable charge. And so the transition metals is orange, and this dark blue here can have variable charge. Well, metalloids, I don't know, because lead, when you think about lead is metal. You know? And so you can say this swap here of elements, variable charge. So these are all fixed charge, so this would be aluminum ion. So variable charge, we look at the periodic table. And when we're looking at the periodic table looks something like this. And so this would be the variable charge region. It goes like this. This is the variable charge. This is a variable charge except for one little L-shaped region. The exceptions here that we have to omit are zinc. Zinc is not variable charge. Zinc is fixed charge. Cadmium is fixed charge, and silver is fixed charge. So these are fixed charge ones that are stuck in the variable charge region. I'm sorry? Nickel, according to your Chem 4 manual, has fixed charge, but it's variable charge. Nickel is +2 is by far the most common charge on nickel.
You know what the other one is?
+3, yeah. So if we look at the nickel, we have nickel +2, which is by far the most common, but we also have nickel +3, and you know what this is? Nickel +4. Whereas silver, cadmium, and zinc, we wouldn't see this at all. So I disagree. I think with the latest revision, I don't know. Krakalici says only one charge, but it's not true. So fixed charge, we got zinc, which is always 2+. We have cadmium, which is always 2+, and we have silver, which is always plus. These are called the 1B group and the 2B group. This is called the 1A group and the 2A group. So the 1A always has +1, the 2A always has +2. Now the 1B should be +1 and the 2B should be +2 on the periodic table. So look, if we take a look at this periodic table, let's see how they numbered this one here to here. You can see it up here. The different numbering schemes here. Here we have the 1B, 2B, we have the 1A, 2A. And so this little L is fixed charge. Everything else is variable charge. And most of them are +2, +3, until we get to this region where it goes +1, +2, and then we get into this region over here, which is +2, +4. Good. And I know you found that pattern there. Good. All right, now what happens if we have variable charge? When we have variable charge, we have to use a Roman numeral in the name. And so let's take a look at an element in this. So some examples would be iron. Iron ion could be either 2+ or 3+. This one we would just call iron, Roman numeral 2 ion. Cation, and this one would be iron, Roman numeral 3 ion. Now the higher charge gets an ic, and so we use Latin name here because ironic sounds funny, so this is called ferric ion. And this would be called, the lower charge one will get ferrous. And so it depends on what the lower and higher charge is. So for example, copper just forms +1 and +2. And so easy, this is copper 1, Roman numeral. This is copper 2, Roman numeral. So copper. There's no space between the name and the Roman numeral. It's to save paper. This one is a lower charge, so this gets cuprous. We don't have to use Latin because the normal name sounds okay. Actually, no, we do. Cuprium. It's not CO. You know what CO is? Cobalt. And this is cupric from cuprium. These are the old style. Ferrous and ferric and cuprous and cupric. They aren't used as much anymore. So whenever we're in this region, we have to make sure we include a Roman numeral indicating the charge, and we have to have this L. Realization that this little L here is fixed charge. So Z +2, cadmium +2, silver +1. What about copper? Well, copper is +1 or +2. What about gold? Now this gets kind of screwed up. Gold is +1 or +, you don't have to have this memorized, +3. Yeah. Mercury is +1 or +2. Yeah, it would be, it's a funny one. Mercury's a very funny one. But Mercury's not what we call monatomic. For example, this would be monatomic mercury, Hg2+. This is called mercury 1, not 1, 2, sorry, mercury 2 ion. Mercury 2 is a higher charge, so this is often called mercuric. The other example is Hg2, 2+. This is not a monatomic. Monatomic means we just have a single atom. This is what we call a polyatomic. Now polyatomics, they have some other things that we need to factor into polyatomics. This one's a bit tricky because this one's called mercury 1. And so this forms like molecules with Hg, 2 Hgs, but each Hg is +1. And if we have +1 and +1, then the total charge is +2. Okay, that's polyatomic, so that doesn't really belong here, the monatomic. So let's look at polyatomic cations next. When I look at polyatomic cations, they look like this. So variable charge, monatomic. Let's see. Polyatomic cation. The polyatomic cations, what people typically do is just memorize these because there aren't that many. And so the easiest thing is to write them down over and over, or flashcards or whatever else. So we'll just start off with that one. Hd2+, this is mercury 1, polyatomic. Can you think of other ones? Polyatomic cation. Now, they don't have to be the same element. They could be different elements. So you'd like to call them a compound, but they aren't necessarily a compound. They're an ion. Compounds are neutral. And so this one, even though you might want to call it a compound, is the ammonium ion. OH is another one, except it's not a cation because it has a negative charge. Can I think of any other? No. These are the two important ones. I can think of a lot of others, but you don't have to worry about those. All right, so those are all the cations. Let's go on to the anions next. For the anions, the same kind of deal. We're going to have the monatomic anion. For the monatomic, what we do is we just look at the patterns in the periodic table. For example, chlorine is fixed charge. Chlorine always has a, you know what the charge on chlorine is? -1, chloride. Bromine's the same. In fact, all of these halogens have the same charge as ions, -1. And then oxygen is not a -1, oxygen is a -2, and then nitrogen is -3. So it goes -1, -2, -3. In other words, these pick up 1 extra electron, these pick up 2 extra electrons, and these pick up, that's how they gain negative charge. They gain an electron. And so something like chlorine normally has how many electrons? Chlorine has how many protons? 17 protons. Depends on the isotope. Are we looking at chlorine 35 or chlorine 37? And so chlorine 35 would have 18 neutrons. Chlorine 37 would have 20 neutrons. So it's 18 or 20 neutrons, depending on if we're talking about chlorine 35 or chlorine 37. These are the two. How do I know? Because I saw it on the table. Otherwise, I wouldn't have been able to predict it. Right? You could predict it's 75% which one. I know it's 75% which one. It's got to be 75% 35 because look at the average. The average is 35.5. Well, anyway, and it's going to have 17 electrons. And so if it gains 1 electron plus an electron, then we're going to form this. This is going to have 17 protons but 18 electrons, so it's imbalanced. We have more negative charge. That's what it gives it. 18 electrons is special. What else has 18 electrons? Argon. Argon is a very stable gas. You know. Argon, argon's more dense than air. I used to use argon all the time. Argon provides a blanket. Let's say you have a chemical. Like, remember the lithium, how corroded it was? That's corroded because it's exposed to air. Well, what if you didn't expose the lithium to air? If you didn't expose lithium to air, it comes out nicely lustrous. So we call that like a modified atmosphere container or map. And so if you stored the lithium under argon, it lasts longer. It's not going to corrode. Now, you know, I was at Trader Joe's, I bought some coffee beans, and I looked. The coffee beans are stored under nitrogen, and so they eliminate the oxygen. Well, that makes sense because oxygen is going to oxidize things, right? Well, anyway, getting back to this, so what do we do? For monatomic, change the ending. Change ending of the element to IDE. So IDE. So chlorine would go to chloride. Oxygen would go to oxide, and sulfur would go to sulfide. And the charges we can just get off the periodic table, you know. So we'll do O2 minus oxide, S2 minus sulfide. And so the monatomics end in IDE. And so if you see the ending IDE, well, that sounds like a monatomic. And so if we had something like phosphide, what would you guess the formula for that is? Phosphide should be the element phosphorus. It's an anion, so we got to figure out what the charge. What's the charge on it? It's going to be P 1 minus, 2 minus, 3 minus. It's going to be P 3 minus. It's going to be P3 minus because phosphorus has 15 electrons, and there's something special about having 18 electrons. And what's special about that, we'll talk about later, but I mean, this is a pattern that we see. This is phosphide, P3 minus. Phosphide. Now we have polyatomic, of course, anions. And so, if you see the "ide" ending, it most likely monatomic, but potentially it's polyatomic. And so, let's go to polyatomic. Now, we have 3 different endings for polyatomics. We have the IDE ending. The IDE ending, the easiest is just to memorize these. There aren't that many. So, for example, OH is an oxygen bonded with a hydrogen, and it's going to carry negative charge. It's called OH minus. OH minus is called, anybody know what this is called? Hydroxide. A very common chemical is drain cleaner, which is lye, L-Y-E, lye, which is made up of sodium hydroxide. This is another one. These are, I'm talking household chemicals. O2, 2 minus. O2, 2 minus, a very common chemical is H2O2. H2O2 is called hydrogen peroxide. So this is called peroxide. There are others, have you ever heard of superoxide? Superoxide is a polyatomic, but it's O2 with a 1 minus rather than O2 with a 2 minus charge. Superoxide. That one you don't need to memorize. Peroxide you do. What else do we have? We have CN minus. This one's called cyanide. Think of any others. Hydroxide, peroxide, cyanide. I'm thinking I'm missing something, but maybe not. You have a list in your supplement, but I don't have the supplement with me right now. Let me make sure I'm not missing anything on your list from the book. I'm not. I think that's pretty much it. All right. We also have polyatomics that end in 8, ATE. The 8. So we have the ides and the 8s. The 8s, we have a pattern that you can use to remember the 8s. Let me show you the pattern that one can use to remember the 8. And so, two categories here. One from periodic table. So, in the periodic table, we're going to start with B, C, BC, boron, carbon, who's next? Okay, we'll go down from fluorine. Fluorine to bromine to iodine. Okay, so we have these ions like borate, chlorate, nitrate. There's no oxide. We have fluorate, chlorate, bromate, and iodate. Uh-huh.
Isn't the carbon carbonate?
Yeah. Carbon's carbonate. Thanks. Oh, I was thinking. Sorry. Carbonate. Borate, carbonate, nitrate. All right. Now let's take a look at the formulas for these. Borate is BO3. So we have one boron, 3 oxygens, and the whole thing is -3. So BO33. Carbonate is CO3 with the charges difference 2-. Nitrate is NO3 1-. Fluorate is FO3 minus. Chlorate is ClO3 minus. Bromate is BRO3 minus. And iodate is IO3 minus. Do you see a pattern? And so normally with this pattern, what we do is we just memorize this one. If we memorize one, and this one's easy to memorize because what group is this? This is group 13 or group 3A. This is 13 or 3A. So 3, you have the number 3. But what do they all have in common? They all have 3 oxygens. So are 8s always 3 oxygens? Unfortunately not. 8s are not always 3 oxygens. That's why we have this other group. This other group, we're going to start with silicon here rather than boron. So we have silicate, and then we have phosphorus, which we have phosphate, and then we have sulfur, which gives us sulfate. And then we can have below here, for example, below phosphorus is arsenic, which we can have arsenate. And below sulfur we have selenium, which we call selenate. There's a pattern to this too. Below silicate we have germanium, which is called germanate. Okay, so let me write out the formulas for these here. Silicate is SiO4 with a 4- charge. This one usually memorize. Silicon's in group 4 or 14, so 4-4. Phosphate is PO4 with a 3- charge. Sulfate is SO4 with a 2- charge. And so there's a little pattern that's going on with these. Now, when we go to arsenic, you think, okay, it goes, this is the pattern I think, 3, 4, 5. And so when we go to arsenate, I'm thinking 5 oxygens, right? But it's not. Arsenate is ASO4. Now what's going on with the charge? Well, the charge stays the same. So take a look. PO4, ASO4, 3-, 3-. And so once we hit this inner block, then it comes out the same. So what do you think selenate is? Selenate would be SeO4, 2-, and you'd be right. And then germanate, GeO4, 4-, etc. It just keeps going down like this. So we have the inner block and this outer shell.
And so these, you know, in general, I just memorize two. I memorize borate and I memorize silicate, and the rest are easy to derive. You can just do it in your mind, like mentally visualize it in your mind. If you look at this pattern enough times. All right, but there are some eights that you just have to use, you know, raw memorization. However you do that. And the other eights that are just memorized. So let's talk about the other eights. Let's memorize these. What are the other eights that you have to memorize? I should have looked at your list so I don't. I'm sorry? Acetate, yes. Acetate's a big one. Acetate. Acetate is C2H3O2 minus. 232 minus. That's one way of memorizing it. That's acetate. Or it has the structural formula, CH3COO minus. Acetate. Okay, then we have chromate and dichromate. That's another big one. Chromate is CrO4, 2 minus. Dichromate is like two of these, but we have to get rid of one of the oxygens. And so Cr2O, it should be 8, but we drop it down to 7 because of the way these two chromates link together. They link together not by an oxygen-oxygen, but it's like the double valve. We drop one of them. And so that it links together with this one oxygen. And the charge, you would think, okay, oh, well, we're going to double the charge, 4 minus, but we don't double the charge. This charge, interestingly enough, stays the same. Okay, and that's because how they're linked together structurally. If you know the structure of this, then it's easy to remember. If you don't know the structure of this, then it's just raw memorization. So this is chromate, dichromate. Oxalate is another big one. Oxalate. Oxalate is C2O4, 2 minus. I don't know, was cyanate on your list? Cyanate. Cyanate's not that common, so you can omit that from the list. Acetate, oxalate, very common. Chromate, dichromate, very common. There's one other that's super common, and it's called permanganate. Permanganate is MnO4, but the charge is only -1. And so it's MnO4 -1. And unfortunately, you got to just memorize those.
Something like this, right?
Yeah, actually, let me just see. Oh, thiosulfate. Yeah. They do have cyanate, thiocyanate. Okay. Well, thank you. Thiosulfate is somewhat common. Thio, do you know what thio means? It means sulfur. So thiosulfate, what you do is you take a sulfate. What is a sulfate? A sulfate is SO4. And oxygen and sulfur are in the same family. And so what we do whenever we see the thio, we replace one of the oxygens with a sulfur. And so let's replace one of these oxygens with a sulfur. If we replace one of the oxygens, then we lose one oxygen. And so it becomes how many oxygens? 3. But we also gain a sulfur, so how many sulfurs do we get? 2. And so thiosulfate is S2O3 with a 2 minus charge. So all we did was we swapped a sulfur for the oxygen. I know these aren't on your list, but these are rare. Cyanate and thiocyanate. These ones don't bother memorizing. Cyanate is CNO minus, thiocyanate is CNS minus. Thio, remember, change the oxygen to sulfur. And so these ones you don't have to memorize. I know they're on the list, but I wouldn't bother memorizing. So we aren't going to encounter those much. Now, we've just saved ourselves a lot of memorization because we have something called the ites, the polyatomic ites. The ites are one less oxygen than 8 same charge. So let's look at SO4. 2 minus is sulfate. SO3 2 minus is called sulfite. NO3 minus is nitrate. NO2 minus is nitrite. Then we have something called the per. The per is a prefix. If we have per, it's usually one more oxygen. One more oxygen. And same charge. So what's this one? ClO3 minus. That one's called chlorate. Therefore, ClO4 minus is called perchlorate. We wouldn't call it perchlorite because perchlorite would be the same thing as chlorate, right? Because, you know, chlorite is one less than chlorate, and so one more than chlorite would be chlorate. Does that make sense? But anyway, this would be it. And then we have hypo. Well, hypo refers to what? More or less? Less. Hypo is less. Hyper is more. And so hypo is one less oxygen. Same charge. So would we ever call something hypoperchlorate? We would never call anything hypoperchlorate because one less than perchlorate would just be chlorate. Could we call it hypochlorate? No, hypochlorate would be the same thing as chlorite. But hypochlorite is something. So if we go to chlorite, chlorite is what? Chlorite's 3 oxygens, chlorite's got to be 2 oxygens. So this is chlorite. And so ClO minus with 1 oxygen is called hypochlorite. Hypochlorite. So we have the per and the hypo in addition. So when we name ionic compounds, well, this is pretty much the name of the ions. We just name the cation first, followed by the anion.
So we just gotta memorize. We don't have to like see how it begin like that.
Yeah, right. You just memorize it, and then we'll look for other patterns later. structural clues and other things. But basically, ionic compounds, for ionic compounds, do not use prefixes. Do not use prefixes. So what I mean by this is this. When we name it, let's say we want to name this MgCl2. We first name the cation, and then we'll put a space, and then we'll name the anion. And so the cation name, this is fixed charge. And so the cation name is just magnesium. And the anion, this is monatomic, so we do not call it dichloride, although you could. This is not magnesium dichloride, it's just magnesium chloride. And so the magnesium is Mg2 plus, chloride is Cl minus. Well, compounds are electrically neutral. And so because compounds are electrically neutral, we could figure out the ratio. Because compounds are electrically neutral, that is, the negative and the positive have to balance each other out, we can figure out the ratio. We can determine ratio without the prefixes. We don't need the prefixes, because if I have a 2 plus, how many of these negatives do I need to balance it out? Will one negative balance out a 2 plus? No, I need 2 negatives. And so if I go 3 negatives, does that work? No. And so 1 negative doesn't work, 2 negatives. So the formula's got to be MgCl2. There's got to be 2 of these negative chlorides to balance out that plus 2. And so we don't have to call it magnesium dichloride because we can figure it out based on the charge of the ions. And so we just do it here. So what would this be called? Would this be called disodium, and then CO3 is carbonate? Would this be called disodium carbonate? No. The name of this is just sodium carbonate. Sodium carbonate. And we know that sodium is fixed charge, +1. Carbonate is a polyatomic. It's one of the H off the periodic table. Carbonate is CO3 2 minus. In order to balance out the charge, how many sodiums do we need? 2. And so it's going to come out to Na2CO3. That'll be it.
You just do it by flipping, like, flip the charts up top and crisscross that slot.
Yeah, you can crisscross them down like that to get the ratio. That works as well. I like to do it this way, but you can always do it that way too. So let's go to something like this. Iron to phosphate. Okay, so here what we do is we figure out what is iron 2, the ion, the formula. It's Fe2 plus. And then phosphate is one of the ones off the periodic table. Is it 3 oxygen or 4 oxygen? 8. There's a 4 oxygen. Then we figure out the charge. Its charge will be 3 minus. And so the flipping one that was mentioned is this. Use these as the subscript. And so this is going to be Fe3PO42. Does that look right? Fe3PO42. Yeah, you got to watch out because this says 42 oxygens and 1 phosphorus. Is that right? No. So we need parentheses here. We want 2 of the phosphates to balance this out. In other words, it's like this. If I have 1 iron and 1 phosphate, do the charges balance? If I have 1 iron and 1 phosphate, the charges don't balance. It's +2 minus 3, it's -1, right? Then I go to 2 irons. Well, if I go to 2 irons, now I got +4 minus 3, the total charge I'm looking at. Plus 4 minus 3 is plus 1. It still doesn't balance out. I need more negative. So I got 2 phosphates. That's minus 6 plus 4 gives me minus 2. Minus 2 doesn't balance out, and then now it's balanced. Plus 6 minus 6. It's balanced. This is going to be Fe3, PO4, and I got to show I have 2 of those, not 42 oxygens, but 2 of the phosphate. And so this is it. This is called iron 2 phosphate. And so let's look at some more examples of naming some compounds here. Unfortunately, I have to leave early. Other questions? I have to leave early today for an appointment, but we'll look at some examples before I leave. Okay, aluminum, is that metal or non-metal? Typically, we think of aluminum as being a metal. And so we named this as an ionic compound or molecular compound? Ionic compound. It makes a big difference because if we consider aluminum a non-metal, we call this dialuminum trioxide because we think of it forms molecules, but it doesn't in this case. It forms lattices. This is called. Are we out of time? Almost. Yeah. Actually, I got to leave pretty soon, but like now. But we'll do more examples of this as we go along. So this is chapter 6.
Tomorrow, do we meet you?
No, we meet in the lab tomorrow. It's going to be uncomfortable, but this room's, I think, occupied by a different class. No, you don't need it. You could just mark your answer on it.